Hello everyone, welcome back. So we've got another example here and we're going to be solving it using our cylindrical and radial coordinate system. Sorry, our cylindrical coordinate system. So what do we have? Well, we have a 0.2 kilogram pin right there, and it's constrained to move in that smooth curved slot with a path that's defined by this equation. Now, the slot arm has a constant angular velocity. If you hear constant angular velocity, remember that means the angular acceleration will be 0. And all this motion is in the vertical plane, so gravity's pointing down that way. We want to know the force of the arm on the pin when theta is equal to 0 degrees. Now you need to draw the 4U by diagram and the kinetic diagrams. Okay, so first off we have to establish where our r theta coordinate system is going to be when theta equals 0. And we're going to have its origin right here at the center. Then we need to draw our free body and our kinetic diagrams. Now, just looking at this one right here, we see our free body diagram. We have weight, we have the normal force pressing up of the pin. We have our acceleration in our transverse direction, we have acceleration in the radial direction. Do you see any forces though over here in the radial direction? What do you think this acceleration is going to be? Well, let's find out. Now, we know an equation for r in terms of theta. And so when we take our time derivative, we have to remember we can use the chain rule. We don't know what dr dt is. But we do know that this should be the same thing as d dt times dr d theta. D theta dt times dr d theta. There we go. And so that's why we bring in our angular velocity right here. And we would do the same exact thing for getting our second derivative of the radial. Now, if we plug in everything we know, where we know that theta is equal to 0, theta dot is equal to -3 radians per second, and our theta double dot will be 0 radians per second squared, we can solve for these three values. And then use those to calculate our our transverse and radial accelerations. Now, here's the thing that might freak you out. Look at this right here. It's -27 meters per second squared. And we saw that there was no force in this radial direction. So where is that coming from? Where is that acceleration coming from? Because it's sum of forces equals mass times acceleration. Well, here's the big thing. We left one out. The wall right here is also going to have a normal force. And it's going to be pressing on that pin. And so that is what's causing that radial acceleration at the last second. Because you've seen it before, just like in our previous example with the ball. As it spins, it's going to have a centripetal force. Now that's for a circular path. This is not quite the same because we have our slot, which is, more of a ellipse. But still, it's a very similar process. So, solving all of our equations, we get what the normal force is of our slot on the pin. And if we wanted to, we could even solve what that normal force would have to be from the wall on the pin. But we weren't asked that, so we're not going to worry about it right now. So, that's all for this time. Thank you for listening, and I'll see you all next time. Bye-bye.